Welcome to this explainer. Today we're going to completely demystify the complex mechanics of human joints. We're taking all that dense, heavy anatomical textbook stuff and transforming it into a super accessible user manual for your body's hardware. Right, let's just jump straight into it.
We've organized everything into 4 logical parts for you. The architecture of articulation, inside the synovial engine, the mechanics of movement, and finally, when the machine breaks.
So, have you ever actually stopped to think about the silent, tireless machinery keeping you in motion every single day? I mean, we all completely take our ability to move for granted, at least until something aches or, pops. But by reverse engineering these biological structures together, we can figure out exactly how they work and how best to maintain them.
Okay, Section 1, the architecture of articulation. Let's establish the baseline blueprint for how the human skeleton actually connects.
At its core, a joint has a surprisingly simple definition. It's literally just the site where 2 or more bones articulate, or come together. That's it. But as we'll see, they definitely don't all swing freely. The amount of movement you get depends entirely on the joint's specific design.
Basically, there are 3 main categories of joints, and they create this sort of hierarchy of mobility. At the very top, we have joints locked incredibly tight with fibrous tissue. These are totally immovable, fixed joints, like the sutures holding your skull together. Then in the middle, we have cartilaginous joints. These are only slightly movable. They use these little pads of fibrocartilage that allow for just a tiny bit of compression, like the discs between your vertebrae. And finally, at the bottom, we have the really fun ones, the freely moving synovial joints. Think of your hip or your shoulder. These give us that massive dynamic range of movement.
Moving right along to Section 2, inside the synovial engine. Let's zoom in on this ultimate engine of movement and see what really makes it tick. Okay, that number 7, it represents something absolutely remarkable. The ends of your bones, the parts that actually meet inside these freely moving joints, are capped with hyaline cartilage. This is your body's ultimate biological shock absorber. And in young people, this incredibly smooth lining can be up to 7 millimeters thick. To put that in perspective, that's incredibly thick for a biological layer with zero blood supply of its own, but it is perfectly engineered to handle immense compression forces and carry your entire body weight.
Now, to keep all of that moving smoothly without grinding, your body has a brilliant self-lubricating system. Synovial fluid is secreted right from the synovial membrane into the joint cavity. It's this thick, sticky liquid with the consistency of a raw egg white, and it acts exactly like engine oil in a car. It completely prevents friction between the moving parts, supplies vital nutrients to that cartilage we just talked about, and it even contains these specific cleanup cells called phagocytes that literally vacuum up microbes and debris. How cool is that?
Of course, all of this internal fluid and slippery cartilage needs to be kept tightly contained. So, enclosing the whole shebang is the joint capsule, a tough fibrous tissue sleeve holding the bones together. It works alongside these structural cables we call ligaments. Together, they give the joint just enough slack to let you move freely, but they remain unbelievably strong to protect the internal machinery. Oh, and we also have bursa. These are clever little sacs of fluid acting as extra cushions to stop friction wherever bone, skin, or tendons might rub together. All right, Section 3, the mechanics of movement. With our biological engine completely built, let's look at the mechanical levers and pulleys these joints actually operate.
Let's translate some of these formal biomechanical terms into real-world action. Actually, try this with me right now. Hold your hand out and turn your palm facing up. That movement right there, that's called supination. Now, flip your hand so your palm is facing down. That is pronation. These are just 2 of the super specific mechanical actions made possible by our joints, alongside the basics like flexion, which is just bending, and extension, which means straightening out.
Let's look at a prime example, the shoulder joint. The shoulder is a classic ball and socket joint, and honestly, it's a total marvel of biomechanical engineering. To give your arm that massive free-swinging range of motion, the shoulder's capsular ligament is basically designed to be super loose. It deliberately trades tight, rigid stability for ultimate flexibility. And because that capsule is so loose, it has to rely heavily on other things to keep it from popping out, like a rim of cartilage called the glenoid labrum, and crucially, your biceps tendon, which literally crosses right through the joint cavity, acting as a dynamic stabilizing cable.
On the flip side, let's look at the knee. It is the largest, most complex joint in the entire human body. It acts as a heavy-duty hinge. So instead of maximizing wild flexibility like the shoulder, the knee is completely packed with internal crossing cables called cruciate ligaments, plus extra wedge-shaped shock-absorbing discs known as menisci. These are specifically built to handle massive weight-bearing loads and stop your leg bones from sliding sideways. Interestingly enough,
the knee can actually mechanically lock when you fully straighten it, which lets you stand up and balance while saving a ton of muscular energy.
And that brings us to section 4, when the machine breaks. This is kind of the climax of our story. What actually happens when this intricate biological machinery wears out, or even worse, suffers a systemic attack.
You know, people confuse different types of arthritis all the time, but the distinction here is absolutely crucial. Osteoarthritis is basically a degenerative disease. It's a mechanical wear and tear issue where that slick, articular cartilage gradually thins out because the breakdown is just happening faster than the body can repair it. It usually targets heavy weight-bearing joints in late middle age. Rheumatoid arthritis, on the other hand, is completely different. It's a systemic, inflammatory autoimmune fire where your own body mistakenly attacks its synovial membranes. It can kick off at almost any age, and it usually goes after the smaller joints in your hands and feet.
Let's break down how this destructive cascade happens step by step with rheumatoid arthritis. If that autoimmune inflammation progresses, it starts with step 1, severe cellular swelling and a bunch of fluid building up in the joint. By step 2, this abnormal layer of granulation tissue, called a pannus, starts growing and actually eroding the protective cartilage. Moving into step 3, that tissue turns thick and fibrous, creating these tight adhesions that really restrict your movement. And tragically, in severe cases, step 4 means that fibrous tissue ossifies. The joint literally fuses into solid, immovable bone.
Now, jumping back to osteoarthritis for a second, it's important to realize that mechanical failure isn't always just about getting older. Actually, scratch that. Secondary osteoarthritis can destroy a joint much earlier in life if its delicate internal geometry gets messed up. We're talking about things like congenital bone deformities, a bad traumatic fracture inside the joint capsule, or even repeated internal bleeding from conditions like hemophilia. All of these can severely damage the cartilage and trigger early, rapid degeneration. Another totally fascinating and, let's be honest, agonizing failure mode is gout. So gout happens when you have an abnormally high level of uric acid in your blood, which is just a normal waste product from cell breakdown. But if your body can't flush it out properly, that acid literally crystallizes inside the joint's biological casing. These sharp little sodium urate crystals trigger a massive acute inflammatory response, usually causing a single joint, very often the big toe, to become incredibly red, hot, and intensely painful.
Which brings us to our final thought. Knowing just how intricate, dynamic, and ultimately fragile your body's biological machinery really is, how are you going to treat your own physical hardware from today onward? I really hope this explainer gave you a profound new appreciation for the silent, tireless machinery keeping you in motion, and leaves you wondering how